I'm going to talk about this study where researchers found that the asteroid that hit the Earth about 66 million years ago and offed all the dinosaurs was a carbonaceous asteroid that came from out beyond Jupiter. And that's the TLDR, so if it's all you wanted to know, hit the like button and scroll on. Otherwise, I'll go more in depth. This is what's called a protoplanetary disk, specifically HL Tauri. And Tauri just refers to the constellation it's in, Taurus. In the center there is a very, very young star. And all these rings are basically circles of hot matter that are orbiting that star. And when I say hot, I mean very, very hot, ranging anywhere from, probably close to 10,000 degrees near the star. And as you go out, we're still talking about in the thousands of degrees. Now, each of these bands has the potential to become a planet or a planet-like body. And beginning on the outside, each of these bands will cool, and as it cools, the ultra-hot matter can start to condense and form little droplets. Those little droplets become little pebbles. Those pebbles start aggregating together, and eventually you get large asteroids. So on the outside here is where it's going to be coolest, and on the inside it's where it's going to be hottest. Also, the heaviest elements and the heaviest minerals are going to fall toward the center. And that's why, for example, in our solar system, the rocky planets are all on the inside, and then you get out here to where Jupiter is and you have a gas giant. Now, all this is the asteroid belt. There's actually not quite enough material there to even make one planet. But you can also see asteroids are spread out through Jupiter's orbit. In fact, all this probably would have formed a small planetoid or something like that if Jupiter's gravity hadn't kept on pulling on all of them. So this is an ordinary chondrite. Chondrites are meteors. You can see all these little dots of metal and minerals. These would have cooled while the solar system was forming and then kind of aggregated together. The bulk of it is made up of silicates, so things like quartz or granite-like material that would have cooled holding all these little spheroids together. And basically, these chondrites are the oldest rocks that have ever been found. So this whole thing would be able to cool and aggregate somewhere around 4,000 to 5,000 degrees Fahrenheit. This is also a meteor, a carbonaceous chondrite, and the difference is that instead of being held together by silicates, it's held together more by this carbon-filled almost dirt-like material. And this would aggregate at a much, much lower temperature. We're probably talking about temperatures below freezing, below the freezing point of water. So in our solar system, you have to get past what's called the frost line in order to get those kind of temperatures. And that frost line is somewhere beyond the orbit of Mars. And the reason we know that is because there's ice that has formed on some of these asteroids out here. However, in the past, that frost line could have been in a different position. Anyway, the asteroid that came down and killed off the dinosaurs, or at least created the conditions that killed them off, had to have been about 10 kilometers wide. And its crater was found to be here in Chicxulub, Mexico. And you can kind of see a little circular ring right here around this part. And that ring, as you can see up in this corner here, that ring extends out into the Gulf of Mexico. And this is an artist's rendition of what it would have looked like at the time. Well, when that meteor hit, it would have sent material from the Earth's crust very, very high. In fact, hundreds of miles into the atmosphere, above the atmosphere even. In addition, the asteroid itself was completely vaporized. It was destroyed. So all that material would have mixed up in the atmosphere and in low orbit around the Earth, and then eventually fallen back down. And all that material created a layer in the Earth's crust. Specifically, this little white line here, this is called the KP boundary, or the Cretaceous-Paleogene boundary. And below this line is where you can find things like dinosaur fossils, and above this line, there aren't any. Interestingly, a bunch of volcanoes were going off in the Deccan Traps in India, and they contributed a lot of material that formed that boundary as well. They kept erupting for somewhere between 500,000 and 800,000 years. So you have actually two events that contributed to this very sudden change in climate. This is another picture of that KP boundary, and it's found all over the world. Basically, anywhere you go on planet Earth, you can find this boundary in the crust. When you look at the elemental composition of meteors, you find that actually they are higher in this platinum group of elements. So platinum, rubidium, rhodium, palladium. And they have about 900 times as much as you just generically find in the Earth's crust. Now, chances are, just because those elements are heavier, they're still in the Earth. It's just they've gone toward the center. And of those platinum group elements, they use the analysis of rubidium specifically to try to determine where this meteor came from. Because like I said, that meteor was completely vaporized and is now spread out over the whole Earth. The reason they selected rubidium is because it has all these different stable isotopes. So they were hoping that by analyzing the isotopes, they could figure out what kind of meteor it was that hit the Earth. They collected a ton of samples from different meteors and different points around the Earth. These are samples from that KP boundary, and they collected them from Europe, Canada, South America. These are samples from other meteors, silicate meteors, specifically those ordinary chondrites. And then these are samples they analyzed from carbonaceous chondrites. They also used for comparison just some samples, regular samples from the Earth's crust. What all these points show is the amount of rubidium that was in these meteors compared with the amount of rubidium that's in the Earth's crust. And you can see that the samples from that Cretaceous-Paleogene boundary are pretty close to the average for carbonaceous chondrites. The next thing they did was they looked at two different isotopes of rubidium, rubidium 100 and rubidium 102. And they looked at specifically what's the ratio of rubidium 102 to rubidium 100 in each of these different samples. Now, this chunk in the blue here, these are samples from carbonaceous chondrites and from the KP boundary. This figure also looks at the proportion of rubidium 100 versus the overall rubidium content of these different samples. Up here are the ordinary chondrites, so the silica-heavy meteors. And down here are the carbonaceous chondrites and the samples from the KP boundary. So based on this, we can say with pretty high certainty that that giant asteroid that hit in Chicxulub, Mexico, was a carbonaceous chondrite. So the story goes, this asteroid would have formed early in the solar system's history, somewhere out beyond the orbit of Jupiter. And then it would have fallen in and eventually found a stable orbit, most likely somewhere within this asteroid belt. And then some gravitational event, most likely from the movements of Jupiter, eventually knocked it out of its orbit. It probably spent many, many millions of years, maybe even a couple of billion years, spinning in an orbit around the sun that continually crossed the Earth's orbit before the Earth captured it and it fell in.